Okay, these are the rough diagrams for AquaTrace. This is the front, the top view, bottom view, and then the front view. Now, first, you can see these large white blocks. These are the magnets. They will be curved, so they curve around the pipe and allow for easy attachment of AquaTrace, and as well as easy movement. You can relocate it really easily. There will also be this kind of shell. This shell prevents like water damage or any gunk from getting onto the board itself, which is under, or the battery. There will also be antenna. This is for this is for uploading the data digitally. And then on the very bottom there will be this sort of vibration sensor. This is where all the data will be collected and processed and then basically sent to upload through the antenna. So again, the magnet for easy movement, the shell for protection, the battery and the board for processing data, and then the vibration sensor which collects the data itself. This is our quick presentation on AquaTrace, our proposed solution to hidden leaks. The current problem right now is that most leaks in pipelines can't be detected, and most maintenance only happen once every several years. This results to up to 30% of all treated water being lost due to these hidden leaks, as well as up to $50 billion per year. Our proposed solution is AquaTrace, a sensor that will attach to existing pipelines, and by sensing changes in vibrations, we'll be able to tell when there is a leak. This way, we can have constant updates on whether or not there will be a leak before extreme water loss occurs due to leaks existing for years. Now, the core technology will be using vibration sensors that will be able to detect change in vibrations. This lets us know when there will be a leak, because when there's a leak, they'll generate a distinct mechanical vibration signature in the pipe wall. Now, this is the leak listener. The AquaTrace node clips onto already existing access points on pipes in mere minutes. There's no need to modify existing pipelines. All it is an attachment. This allows utilities to cover entire neighborhoods without any expensive permanent hardware or any large-scale changes in the pipelines. Now, in terms of architecture, we'll be using three forms: the attachment, the sensing, and the connectivity. For attachment, we'll be using magnetic attachment, which prevents signal dampening, as well as easy relocation. For sensing, we'll be using high sensitivity contact mics, which capture structural vibration and lets us know when there's a change in the vibration. And for connectivity, we'll be using low WAN, enables long range, low power data transmission, which allows us to transfer the data that we've received from the sensors. Now, for precision analytics, we'll be using probability scoring, which evaluates how likely it is for a leak to be somewhere in the pipe system. We'll also use stability tracking because real leaks are persistent. We'll filter out intermittent noise, such as traffic or usage, by tracking these patterns over days. And lastly, we'll use actionable intelligence. An output is a clear, likely leak alert and not messy waveforms that are hard to understand. And using all of this, we'll be able to generate AI-generated probability heat map, which lets us know where leaks are likely to be. Now, why does this issue even matter? Now, why does this solution even matter? So this solution provides continuous protection from leaks. One, conservation. It leads to significant reduction in water loss because we're constantly monitoring. Also, reliability and prevents catastrophic main breaks because we have constant sensing. And lastly, sustainability. It's better stewardship of scarce resources because we're using existing pipelines.
All right, so this is a code for which that AquaTrace will use to operate, and initially you can see that Google Drive is mounted, and then we have some basic CSV paths. Here you can see the accelerometer data CSV, and then we import scikit-learn. So we'll be using the algorithms from sklearn to power our ML model. You can see logistic regression and gradient boosting classifier both being imported here. And then initially there's just some CSV readings and schema detection software. So once that ends, you have our features and windowing. So you can see that there are these features that are being imported. You have the time domain and frequency domain features such as centroid, time kurtosis, RMS, etc. And then we just have our simple train and test split. So this is a basic 75% train, 25% test split, and it's just done through pandas. So we have a pandas data frame here. You can see that. And then the model training begins. So we have logistic regression and gradient boosting classifier. You can see these hyperparameters have been trained after much testing. So this is to optimize the precision recall curve and our target normal recall. So yeah, that's what these hyperparameters are tuned for, and this powers our algorithm. And then you have a threshold. So the model outputs a probability, and we set a threshold to optimize the leak detection. So it's a cutoff to determine whether it will be classified as leak or normal. Then finally, you just see some basic statistical output. That's all. Thank you.